So have you ever wondered how an AI can learn to master a game or figure out how to control a robot without someone programming every single possible move? Well, today we're diving into Q-learning, a really cool algorithm that basically lets an AI teach itself through nothing but trial and error. The whole problem that Q-learning was built to solve is this idea of learning without a map. Just picture it. An AI agent is dropped into a totally new world. No instructions, no guide, no idea what the rules are. It has to figure everything out on its own. Okay, so imagine you're in a maze. But here's the catch. You're blindfolded, you don't have a map, and you don't even know what a wall feels like until you literally bump right into it. How on earth would you find the exit? That is the exact challenge our AI is facing.
And this isn't just some abstract maze puzzle. This is the very same challenge a robot faces when it's learning to navigate a chaotic factory floor, or an AI trying to master a video game it's never seen before. The only way to learn the rules is to start playing.
The solution is this really elegant algorithm called Q-learning. It's a type of reinforcement learning, which is just a fancy way of saying it learns from feedback. Getting rewards for good moves and penalties for bad ones. But what makes Q-learning so special is that it's model-free. All that means is it doesn't need a map or any pre-built knowledge of the world. It builds its entire strategy from scratch, just from experience.
So how does it even remember what works and what doesn't? Well, it builds a kind of memory, an internal cheat sheet that keeps score of every possible move it can make.
And this cheat sheet has a name, the Q table. Think of it like a giant grid. It lists every single place the agent could possibly be. We call that a state, and every possible move it can make from that spot. Then, each entry in this table gets a score, a Q value, which is just an estimate of how good that move really is.
Now, when our agent first starts out, its cheat sheet is totally blank. Every single Q value for every action and every state is just 0. This represents complete and total ignorance. The agent has absolutely no clue what to do. It knows nothing.
So, how does it go from being a blank slate to an expert navigator? Well, it fills in that table using a really simple but powerful loop: trial, error, and reward. It literally just starts moving and learns from the consequences.
The whole process is basically a 4-step dance that just repeats over and over. First, the agent picks a move. Second, the environment gives it some feedback, either a reward or a penalty. Third, it uses that feedback to update the score on its cheat sheet. And finally, it moves to the new spot and does it all over again.
But here's the crucial part. The agent doesn't know these rules ahead of time. It has to discover them. Every time it takes a normal step, it gets a tiny penalty, a -1, which encourages it to find the shortest path. Hitting a wall? That's a bigger penalty, -5. But reaching the goal, that's the jackpot, a massive +10 reward.
Okay, let's watch its first step. It's at the start, position 0, 0, and it just randomly decides to move right. It gets that -1 reward. Then, the algorithm updates the Q table, but not by the full amount. It uses something called a learning rate. So the score for moving right from 0, 0 is now, say, -0.5. And just like that, the very first piece of knowledge has been created.
All right, next, from its new spot, it tries to move down and bam, it smacks right into an obstacle. The environment gives it a much bigger penalty of -5. So the Q table gets updated again, and the score for moving down from 0, 1 becomes a very negative number, like -2.5. The agent is learning, okay, note to self, that was a bad idea.
So the agent just keeps wandering around, right? It's filling its table with a map of what not to do. Little penalties for normal steps, bigger ones for walls. It's basically a whole landscape of negative numbers. But then, after who knows how many random moves, it just stumbles upon the goal. And it gets the ultimate feedback, a huge positive reward of +10.
This is the breakthrough moment. The agent was in the square at 3, 2. It took the action right, and it hit the jackpot. For the very first time, a bright, positive value shows up in its Q table. A score of 5.0 now marks that specific move as being really, really good.
And that first positive value is a critical signal. It's like a beacon of light in this dark maze, basically screaming, hey, something good is over here. This single number is the key that's going to unlock this entire puzzle.
And this is where the magic really happens. That reward doesn't just stay in one spot, it starts to propagate backward. So the next time the agent is in the square before the goal, the algorithm looks ahead and sees the high value of that next step. It then updates the current square score, giving it a piece of that future reward. This positive signal just flows backward through the maze, trial after trial, lighting up the best path.
Okay, so now that the agent is actually learning things, it faces this classic dilemma. Should it keep exploring randomly, hoping to find an even better path, or should it just exploit the knowledge it already has to get the best reward it can right now?
This is handled by something called an epsilon-greedy policy. It's a balancing act. Most of the time, it exploits its knowledge by picking the move with the highest score from its cheat sheet. But every so often, with a small probability we call epsilon, it explores by trying a totally random move, just in case there's an even better path it hasn't found yet.
After thousands and thousands of these attempts, this constant dance between exploring new things and exploiting what it knows, the agent's cheat sheet is completely transformed. What started as a table full of zeros is now this rich, detailed map of high and low scores that perfectly models the maze. The agent has gone from knowing nothing to being an expert.
And this is the final result. If we turn off all the random exploration and just tell the agent, hey, in every square, just pick the move with the highest Q value, it will follow the absolute best path perfectly every single time. It has learned the single best set of directions to get from start to finish.
This maze example might seem a little simple, but the logic behind it is incredibly powerful. The exact same principles of states, actions, and rewards can be applied to much more complex problems in the real world.
Of course, basic Q learning has its limits. I mean, for a game like chess, the cheat sheet would have to be so mind-bogglingly huge you could never store it. That's why modern AI uses extensions like deep Q learning, which actually replaces that giant table with a smart neural network that can just approximate the scores. This lets it tackle enormous problems.
And that is really the key takeaway here. Q learning is the foundational concept that made all of today's advanced reinforcement learning possible. It established these core ideas of learning from interaction, from rewards, and from pure experience, which are now at the very heart of some of the most powerful AIs in the world.
So this leaves us with a pretty fascinating question. If this simple logic of trial and error can let an AI master a maze without ever seeing a map, what other incredibly complex problems in our world could it learn to solve next? Could it discover new drugs, optimize global supply chains, or find new ways to design materials, all by learning from its own virtual experience?